In this video, we will be talking about Dijkstra's algorithm. Let me try to explain to you what Dijkstra does. So, Dijkstra's algorithm. Dijkstra's algorithm. Unlike BFS, so let me put it in context. In BFS, it tries to give you the shortest path. However, the shortest path is not necessarily the cheapest. Sometimes you would even prefer a longer path for so long as it's cheapest. A good way to think about it is if there's a direct flight from Philippines to Singapore that costs more, but you were able to find a flight that goes to Singapore but first goes through Indonesia, then Singapore, and then it's cheaper, then perhaps you would want to choose that. So Dijkstra gives you cheapest or fastest path, lowest cost path. How does it do it? So say for example, we have a starting point, and then there's a path from the starting point to A, there's a path from the starting point to B. This is the end point, this is where we want to go. And then there's also a path from B to E. Let's give it some cost. Say for example, S to A would cost you 6 units of monetary resource, and then A to E would cost you 1. Start point to B would cost you 2 units, and B to E would cost you 5 units of resources. This is not a problem because any path you take, say for example, if I take SAE, I still end up with 7 as the total cost. If I take SBE, I still end up with 7 as the total cost. Let me try to add another path here and give it a cost of 3. This sort of changes the optimal solution for the problem, because now I might consider taking the path SBAE because I am able to reduce the cost. 2 plus 3 is 5 plus 1 is 6. Essentially, I have a longer path, sorry, not B, boop 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 boop, SBAE, but the cost is minimized. The cost is 6. And this is where Dijkstra shines. Dijkstra says, you know what, at every step, so at every step from your starting point, you want to be able to look at the cheapest node first, then see if there is a path and see if there are shorter paths for every node that you encounter from that cheapest node. What is Dijkstra saying? So you begin, if you begin with say S, that's your start. This is where I start. So this particular Dijkstra execution is concerned with S. From S, what do I see? That's my first onion. What do I see? I see the elements in the second onion, mainly my first level friends or first level venues. So, is there a path from S to A? So these are my nodes. What am I doing? Undo. These are my nodes, and these are, I'll try to put the cost here. So from S to A, what can I see? I have the cost of 6 from S to A. I can also see B, because from S to B, at my first step, I know the cost is 2. However, if I am in S and I need to find the distance to E, I cannot yet see it because I cannot yet touch it. So in that case, the way to represent it in the Dijkstra iteration is infinity, because we don't know. For all we know, hindi natin siya we can't reach it. And so infinity is there. Now Dijkstra tells us to look at, so that's the first iteration complete. What do you do next? You look at the cheapest node. This is a cheapest node. So let's try looking at this. From the cheapest node, what do I see? From B, I can see A, and I can see a distance of 3, which means that from B of distance 2, I can add 3 to it to get to A. So that would mean I have effectively found, and I compare it. What's my previous knowledge of the path to A? My previous knowledge of the path to A is S to A, 6. But here, if I go from B, if I go to A through B, I get 5 as the cost, which is lesser than the path that I already know in order to get to A. So we update that value. As a convention, when you're looking at a particular place, you don't really get to update it because the distance from where you are to where you are is just the same. From B, what could I also look at? So I can look at my friends, this is A and B belong to the first level, but we can also see E through B. And the distance from B to E would be whatever distance it already has, B, plus the distance that I can see. And so 2 plus 5 becomes 7. What do we do next? Notice that here I've only just looked at B in the first level. So I've already looked at S, okay na siya. I've already looked at B, okay na siya. But in the first level, I haven't yet looked at A. So we don't proceed to E. We proceed to looking at A. So here, I'm looking at A. Now, what can A see? What can A see? What can this node touch? It can touch E. So it knows that the distance from it to E is 1. And the previous distance that we know on how to get A is 5. So 5, my previous distance on how to get to A, plus 1, the new distance of E would be 6, because it's 5 plus 1. So we try to update this because our previous knowledge of E's distance is 7. So let's make it 6 because that's a better distance from A. And then because we're in A, the distance from we're currently looking at A, the distance from A to itself is just the same, so we don't update it. Can I update the distance of B from A? We can't, because the arrow is pointing to A. There's no arrow pointing from A to B, so we don't have to update B anymore. B just stays the same. And so here at this particular point, what can we see, or what can we do next? Well, technically we still have to process E because we haven't yet looked at E, right? We have to look at all nodes. E is the one at the second layer of the onion, second level friend. However, E does not really point to anything. There are no other nodes, and hence we just copy the values that we already got. And here the way to interpret this is the values that you get here are the shortest distance from the start point to the particular edge, to the particular place, to the particular node. So say for example, the distance from S, your starting point to A, is 5. Right? That's from S to A, the best distance is 5. Where you don't go from S to A directly, you go from S, B, A. S, 2, 3, 5. The best distance from S to B is 2. S, B, 2. The best distance from S to E is 6. Where you go from 2, 3, 6. Okay? 2, 3, 1, 6. Now, I was able to trace what I needed, my path to go to the best distance, but really this point of the Dijkstra, or this basic version of the Dijkstra, just tells me the cost of the shortest path. I wasn't really able to get this yet because we did not take note of the path, the parent. If I go to this node and I get this cost, where did I come from? We did not take note of that. And so in the next video, we'll try to give you a problem that takes note of the parent so that we can retrieve the path of the cheapest path, so that we could retrieve the order of nodes that you need to visit in order to traverse the cheapest path. Okay, so that is Dijkstra. But I think in summary, the way to understand, or the thing to remember is BFS, shortest path. When you now add weights to the paths, then you have Dijkstra. And right now what we can get is the total cost of the cheapest path, but we haven't really found the path yet. In the next video, we will try to show you how to get that path. Thank you for watching. See you in the next video.